Welcome everyone to Developing DSLs with Functional Programming, exploring 3 strategies through examples with Ziyang. We're so glad that Ziyang could join us today. With no further delay, over to you, Ziyang.
Hey guys, I'm going to talk about DSL, so domain-specific language. By the way, very happy to be giving this talk because as someone who enjoys functional programming to a great degree, it's a real pleasure to be giving this talk at Functional Conf. And as you know, functional programming is a great choice for implementing DSLs. So a good way to talk about something, I think, is to compare a few different approaches and study their pros and cons. I think that's the right approach. I mean, when I learn a new concept, I often have the question of like, how does it compare to this or that? So doing some comparison can be really helpful. Now, before we do that, let me get a basic question out of the way, which is, what exactly are DSLs? So this is actually a question I got from one of the PC members of this conference, which is along the lines of, you know, when you talk about DSLs, what exactly are you talking about? How do you distinguish it from things like libraries? And I think that's a totally fair question because DSL, domain-specific language, is not a very, well-defined term because, a lot of things can be considered domain-specific and a lot of things can be considered language. So it's worth, doing some clarification. So the way I think about it is in terms of a spectrum of things. So here are some examples. By the way, this is not the only way to view it. I think probably a more precise way to see this is through a 2-dimensional space. But to simplify things, let's just consider a 1-dimensional spectrum, where on the left end of the spectrum, you have things that people typically call libraries and APIs. For example, you can say a hash map library is a DSL for interacting with hash maps. And that is, technically it's not wrong to say that, although most people would probably not call it a DSL, they would just call it a library because it doesn't really look like a language. And as you go towards the right of the spectrum, you start to see things that look more and more like languages. And what I mean by that is that you start to see more and more programming language elements that starts to appear, things like bindings, control operators, recursion, perhaps user-defined functions, user-defined data types, and ASTs and compilers and things like that. So the more you go towards the right, the more you see these kind of things. And the things on the far right are basically just general purpose languages like Haskell and Erlang. And they can also be called DSLs. For example, some people say Haskell is a DSL for denotational semantics, and Erlang is a DSL for distributed computation. And again, it's not wrong to say that, although most people would just call them general purpose languages. What this talk focuses on, I would say, is things that most people would consider more of a DSL than anything else, which is basically most of the middle of the spectrum, but not including the far left and the far right, because if we want to talk about how to design or develop an arbitrary library or API, that's really a different topic, and it has very different considerations. Similar with developing general purpose languages is a totally different topic. For example, for DSLs, one popular approach is embedded DSL, but that's not something you do when you develop a general purpose language, right? So just a upfront clarification on the scope of the talk. So with that said, let's start by looking at these 3 approaches that we're going to explore further in this talk. So we have standalone DSL, embedded DSL, and subsets of general purpose language. Like this 3rd approach is kind of interesting because it's relatively least known and least used, but it can be a very good, it can work very well when it is a good fit. And I'm going to cover that in a bit. So here are some examples of each strategy. And I'm going to put the link at the end so you can check them out if you're interested. The examples on the right are from a specific domain, which is Cardano smart contracts. So this is the logo of the Cardano blockchain. And this is the domain I work on at my current job. And so all these languages are scripting languages for writing smart contracts on Cardano. This is an interesting domain because in this domain, you can find multiple examples of each strategy. So this makes it a very interesting domain to study this topic by comparing these languages. All right, so let's start by looking at approach number one, which is standalone DSL, also called external DSLs. These are essentially new languages developed from scratch. Right, so and here are some reasons why standalone DSLs are attractive. So number one, they are obviously highly customizable for your domain, because if you design a new language, then obviously you can design it however you like. And then it doesn't carry any baggage or limitation from a host language, because you're not using any host language. Right. So that's the strength of standalone DSL. But on the flip side, there are some drawbacks of standalone DSLs. So number one, from a language developer point of view, developing a standalone DSL is often a lot of work, because you need to build a lot of things from scratch. For example, the entire compiler and perhaps a runtime system. And these are already hard enough, but there are some additional pieces you need to deal with, like tooling, for example. If you need some kind of debugger for your language, or if you need some kind of testing framework for your language, or if you need some kind of metaprogramming capabilities for your language, these all needs to be developed from scratch, which is a lot of work. And also library ecosystem, documentation, and so on. Documentation also, often takes a longer time than people expect, but it's important for a standalone DSL because it may be the only learning resources for the user to learn the language. So that's number one. Number two is from a user's perspective. Learning a new DSL can be harder than anticipated. Even if the syntax of the language is not very complex, because of these reasons, like scarcity of learning resources, past experiences may not be helpful, and knowledge learned may not transfer well. So on this point, there is a article that I read on management that said something like, how do you as an employer retain good employees? Well, you should do something that is seemingly counterproductive, which is you should help your employees increase their market value and make it easier, not harder, for them to find a new job. And that may seem counterproductive, but it really makes a lot of sense. And one way to do that is to help them learn things and acquire knowledge that transfer well to other domains and other jobs. And learning a new DSL, the knowledge you acquire may not transfer that well. So, and of course, the last point, anytime you introduce additional language to your team, there's always additional complexity, additional learning curve, additional tooling, additional cognitive load, etc. So basically, learning a new DSL can both be harder and less rewarding than expected. And so these considerations lead to this point that I'm underscoring here, which is standalone DSLs are excellent choices for low-level languages and compilation targets, which may be a little counterintuitive to hear at first, but not really if you think more about it. Basically, at the low level, there are just more reasons to customize things. For example, from a compilation point of view, a small and custom language is often easier to target. I mean, it can be much harder to compile a surface language to another surface language, because different surface languages may have different ways of abstracting things, and there's also often additional dependencies and so on. So that's making compilation easier. And from a runtime point of view, you also get some flexibility on the runtime. You can customize your runtime and make it as efficient as fit as possible. And then a small or minimal and customized language is often easier to reason about and formalize. And this is very important for low-level languages, because you really want your low-level core language to be correct. Because if your low-level core language, on which a lot of things depend, has a design flaw, then it can be pretty hard to fix without disrupting a lot of things. And then lastly, when you use a standalone DSL as a low-level language, you avoid some work required for building surface languages. For example, you probably don't need an IDE or a linter or a debugger for your language, because people will not be writing it by hand. So these are why standalone DSLs are good choices for low-level languages, but exercise caution when using them for surface languages. So if your domain has a requirement for both a low-level language and a surface language, it's often good to use standalone DSLs for your low-level language, and one of the other two approaches I'm gonna cover later for your surface language, and that's often a good combination. So I'm going to show you in a second some examples of standalone DSLs, but before I do that, I just want to make a quick point here. So I mentioned earlier that learning a new DSL can both be harder and less rewarding than you think. And here I just want to make a contrasting point or the opposite point, which is learning to write basic and simple programs in a popular general purpose language is often easier than you think, even for something like Haskell. And I say even for because Haskell is a language that's generally perceived to be hard to learn. And it's also not even that popular. Like right now, it ranks number 27 on GitHub and has a pretty small and declining market share. But even for language like Haskell, from my experience as a Haskell developer for the past almost 7 years, to onboard someone to learn to write some basic and simple Haskell is really not that hard, and not as hard as many people think, because of a few reasons, like abundance of learning resources, at least compared to most DSLs, right? Like there are quite a few very good introductory books on Haskell, and also AI. I mean, the advent of AI makes this even more true, if not much more true, because large language models like ChatGPT, they are pretty good at doing basic Haskell, like reading, writing, answering basic questions. Of course, as your questions gets more and more complex, the quality of answers given by AI starts to decline dramatically, in my experience, which is not surprising. For example, the other day I asked ChatGPT, how do you detect in Haskell whether something has been evaluated to weak hat normal form? And it basically totally crashed and burned. It confidently gave me a totally wrong answer. But that's fine, that's okay. But if you just want to learn to write some basic Haskell, then AI is pretty good at teaching you how to do that. And then Haskell has a good library ecosystem, which makes a lot of things easier. And then on top of all that, when you learn something like Haskell, the knowledge you learn is highly transferable. I talked about transferable knowledge before. It's highly transferable, and it's not just transferable in the narrow sense of writing Haskell itself. It's also in the sense that it just makes you a better programmer in general, because for many people, Haskell is kind of a totally new programming paradigm. And so it will give you a lot of new perspective on how to do things and how code can be written. So just want to make this quick point before we continue. It's not necessarily super relevant to standalone DSL per se, but it will be more relevant later when I talk about the other two approaches. Okay, now let me go ahead and show you some examples of standalone DSLs. The first example I have is a language called Untyped Plutus Core, UPLC. So this is a language that developed by my team and my current job, and it is a low-level smart contract language for Cardano, and it's based on untyped lambda calculus. So here is a example UPLC program. You don't need to understand the program because it's a low-level language. It's not supposed to be easily understandable. So what this does is that it takes a list of integers and it returns the first integer that is smaller than 10. So if there's a type, so this is untyped language, but if there was a type, it would be from a list of integer to maybe integer. Right. So as you can see, this is pretty low-level stuff. You can't really see any list here or recursion or loop or anything like that, because these have all been compiled down to something more primitive. For example, recursion here is encoded using a fixed point operator. As you can see, there's this self-application on the first line, this lambda s to ss. That's basically part of the fixed point operator that encodes recursion. So this is UPLC. Now the question is, why is UPLC a good fit for this particular domain as a low-level language? Well, it basically goes back to the reasons I said earlier about why standalone DSLs are suitable for low-level languages. So UPLC is good at what it is supposed to do. which is validating transactions on Cardano. And it also matches Cardano's philosophy, because Cardano's is a blockchain that emphasizes immutability and determinism. And so a functional language based on lambda calculus would be naturally a good fit. So it's a very good fit for the domain. And it's also very small. It's such a small language that the evaluator of the language fits on a napkin. And this is not hypothetical. This is literally the case. This is the picture of a real napkin that we made. And what we print on the napkin is the specification of the evaluator of UPLC, which is called the CEK machine. And this is the specification of the CEK machine. And as you can see, this is fits nicely on a napkin with plenty of room to spare. So because of it's such a small language, it makes it easier to reason about and formalize and make sure everything is correct. And also, it is also well-researched and stable because it's based on untyped lambda calculus, which has been around for decades, and there's a very large body of research on it. So this gives it a good, solid theoretical foundation and makes the language stable, because it's good because it means we don't need to keep evolving the language over time. Because if we keep evolving low-level language over time, then every time we change something, then all the compilers will need to be changed and so on. So it's very disruptive. And on this point, here's a quote from Professor Phil Wadler. He says, "How do you make sure your language won't be obsolete in 40 years? Well, use one that was invented 40 years ago and use one that was discovered twice." So he was talking about not UPLC, but a typed variant of UPLC called TPLC, typed Plutus core. Because originally our low-level language was typed, and later it became untyped. So typed Plutus core is based on System F, or polymorphic lambda calculus. And System F was discovered in the 1970s, which was about 40 years ago. And UPLC, like untyped lambda calculus, was discovered even earlier than that. So it will be even more true for UPLC. So this is the first example, untyped Plutus core. The second example I have is a very different category, which is configuration languages like JSON and YAML. These are also standalone DSLs, and they can do configurations and other things. So because most people are already familiar with them, so I'm not going to spend too much time on it. But one thing worth noting is that these languages like JSON and YAML, they are also very well suited to be compilation targets, just like UPLC, because they are human readable. So people may think of them as something that needs to be written by hand, but that's not the case. I mean, they are very suitable as compilation targets. You can write your config code in a high-level programming language, hopefully a language your team already uses. So you deal with one fewer language, and then compile your config to JSON and YAML. Because most programming languages are perfectly capable of writing configs. So why not? And you can often do so in a way that is safer and less repetitive. Imagine you need 100 similar YAML files, right? I mean, one counter argument would be separation of code and config, which is true, but it doesn't mean that they cannot be written in the same language. You can achieve your separation, for example, by compiling and running your config code at a different time or a different stage than compiling and running your main code. And that's as good a separation as writing them in different languages. So this is second example. Now I have one last example of standalone DSL. So this is a language called Aiken. This is also a purely functional language, and it is a high-level language for Cardano smart contracts. So this is a surface language, and it compiles to UPLC. So Aiken is a very good example of a standalone DSL as a surface language. So even though it is a new language, it does a number of things to make it easier to adopt. For example, it adopts this standard curly bracket syntax, which makes it familiar to a broad audience. And it also does a number of customizations to make it as easy as possible and as nice as possible to write code in this particular domain, like certain keywords and certain coding patterns and certain like code structures and things like that. So I'm not going to go into details of this code because it's just going to take too much time. But I'll just say that the things I said about using a standalone DSL as a service language, the drawbacks of doing that, still apply. But if you decide to do that anyway, then Aiken is a very good example to study from. It's a very nicely designed and documented language, and it's also pretty popular. It's probably the most popular Cardano language as of right now. So this is Aiken. Now let's move on to approach number 2, which is embedded DSLs, also known as internal DSLs or often just EDSL. What this is they are basically like libraries written in the host language for manipulating abstract syntax trees, ASTs. That's what they are. So, and here are some reasons why, EDSLs are appealing. So EDSLs can be very attractive if your team is already using the host language, because then obviously you can reuse a lot of tooling and knowledge and infrastructure of the host language. So that's number 1. And number 2, even though EDSLs are implemented in a host language, it is still highly customizable for whatever your domain is, because I mean, of course, in terms of syntax, you are somewhat constrained by what your host language allows you to do. I mean, some host languages allows more customization of syntax than other host languages. But in terms of things like programming model, they can totally diverge from those of the host language. Your host language may be functional language, but DSL may be a imperative language. That's totally fine. There's nothing wrong with it whatsoever, because your EDSL is essentially just a new language. It has its own AST that's totally separate from your host language. The only thing you reuse from the host language is the syntax. So your host language is functional, your EDSL is imperative. Perfectly fine. There's nothing wrong with that. And number 3, among all these three strategies of developing DSLs, EDSL is often the easiest to develop and maintain and document, especially when your host language is a statically typed functional language. Because, statically typed functional languages are, they excel at manipulating trees, and EDSL is just libraries for manipulating trees. So it's a really good fit. And so this approach is very well suited for an MVP or proof of concept. And also, if your domain is big and has a large number of users, and different users may prefer different host languages, you can often relatively easily embed the same DSL in multiple host languages, which gives more choices for the users. Okay, so all of that is well and good, but here's the main drawback of EDSL, which is that AST construction and manipulation are exposed to the users. And what I mean by this is, when you write code using an EDSL, you're not writing regular code, normal code in your host language, but you're writing some very specially custom for manipulating ASTs, which usually has a then operator on top, which just takes 2 ints and returns a bool, which is very, very simple. But when you're writing code in an EDSL, what you do is you're often using something like the operator on the bottom, which has a slightly different name, because to avoid name clashing. And instead of taking 2 ints and returns a bool, it takes 2 ASTs representing integers and returning a new AST that represents a bool. So that's what it often entails when writing programs in EDSLs. Of course, the EDSL, the library, will often try to hide as much of this complexity as possible, but some of them will always leak to the users. And here's a quote on this point from Conal Iliad. So this is from his paper, Compiling to Categories. He says, additional efforts can hide more of these symptoms, but the cracks still show, and each new coping mechanism leads to increasingly mysterious type errors. So this is Conal Iliad. Now, to make things more concrete, let me show you 3 examples. These are 3 different languages. They are all EDSLs embedded in Haskell. So the first example on the left is a language called Plutarch. Plutarch is another surface language for Cardano smart contracts. So like Aiken, it also compiles to UPLC. And it is a Haskell EDSL, and this is a Fibonacci function implemented in Plutarch. Oops. Yeah, this is a Fibonacci function. So as you can see, this is not normal Haskell. It doesn't look anything like regular Haskell because everything is different. So instead of integer, you're using p integer. Instead of a regular function arrow, you're using this, this customized arrow. And instead of if then else, you're using this p if, and the equality operator is also different. So everything is different. And so to learn to write programs in a language like Plutarch, it's like you need to learn 2 languages. So you first need to know some Haskell, and then you need to learn this entirely specially customized way, very special way of writing Haskell that is only applicable to Plutarch. So that's Plutarch. The second language in the middle is a language called Copilot. This is an EDSL for processing streams of events. And the compilation target of Copilot is C, so it compiles to C. And as you can see, this one, the syntax is more regular. So it looks like regular Haskell, but it's because it is using a language feature called rebindable syntax. It's a language extension which allows you to redefine or rebind or customize some of the built-in Haskell syntax. So for example, there's this if then else thing in the middle. So this is the regular Haskell syntax for if then else, but it is not the regular Haskell behavior or semantics for if then else. The behavior or semantics are customized by the DSL. So under the hood, it is doing very similar thing. It is still manipulating ASTs, but on the face, it looks more like regular Haskell. So in a sense, it's nice because on the surface, it looks more regular syntax and less noisy. But on the other hand, using rebindable syntax can make things more obscure and less explicit, and it can be harder for you to tell what the code does, and can also make compilation errors worse. So rebindable syntax is kind of a double-edged sword. It's not always a good thing to do. The third language here is on the right is a language I worked on at my previous job. It's also an EDSL targeting C, and it is for writing flight control systems. And this one, as you can see, it has a pretty similar vibe to Plutarch. It is also basically explicitly manipulating ASTs. As you can see, there's this F, this lowercase f, appearing everywhere. So F double, F32, and so on. So this F is basically an abstract type parameter that can be instantiated to some kind of concrete AST type. It's abstract because so that it can also be instantiated to something else. For example, it can also be instantiated to identity, which gives you a program you can run in Haskell. So this allows you to run the same program in Haskell and in C, which is convenient. But other than that, it feels very similar to Plutarch. This also has its own if then else operator called k if then else, and also has this custom comparison operator, as you can see here. So this should give you some idea of what it likes of working with EDSLs. Basically, they are, like I said, they are just libraries for creating and manipulating abstract syntax trees. So I think that's the main drawback of EDSL, which is very complex and specialized syntax. But here are some other additional two drawbacks. So number one, it can be challenging to produce readable target code or develop debuggers, because to do these things, you need to have access to source code information or source code facts, like line numbers, variable names, module names, function names, and so on. So a regular library written in the host language does not have access to those information. Even if it can be made to work, it often adds additional complexity or syntactic noise to the surface language. Then, you don't always need to produce, so it's useful line. And also the host language's library ecosystem provides limited or no value for the users because the users are not writing regular programs. They are writing a very specialized kind of program. Okay, so that is EDSL. Now let's move on to approach number 3, which is called subsets of general purpose language. This is, I think, the most interesting approach. And it's, like I said, it's relatively least known and least used. But when it is a good fit, it can work really well. Reusing the host language ASTs. Because if you're already using a host language anyway, then can you just, because your host language already has compilers and ASTs, so can you just reuse those as opposed to developing a new AST and new library to work with them as you do in EDSLs? And indeed you can, at least sometimes you can. And what this allows you to do is that this will make your DSL a subset of your host language, which means to compare two ints, you just need to use this regular greater than operator because now your DSL is just a subset of your host language. So this allows you to write basically simple and normal programs in your host language. Now, the question is, how do you access and reuse your host language ASTs? Well, there are mainly two ways. One is metaprogramming. So metaprogramming is one way to manipulate your ASTs, and this approach is called, so DSLs developed through this approach is called QDSL. Q means quoted or quotation. Right? Quotation is a terminology in metaprogramming, meaning turning source code into ASTs that you can then work with. So QDSL is one approach, but in my opinion, this approach has a number of issues. For example, it only allows you to access the surface language ASTs, which is often a very big data type, because the surface language often has a lot of syntactic sugars or multiple ways of doing the same thing, and these all needs to be part of the AST definition. So it usually has a very large AST and makes it harder to work with. And it also suffers from much of the same issues with EDSLs, which is like heavy syntactic noise, and you're not doing regular programming and so on. As you can see from in a second from the example I'm going to show you shortly. So the second approach for reusing your host language AST is compiler plugins. And this is an approach that I think often works much better. For example, it allows you to access both the surface AST and the lower level AST, core AST, which is often a much smaller data type. And so basically this solves all the problems of metaprogramming and can work much better and gives you true subsets of your host language. And I also have some examples of this in a bit. So to show you a comparison between surface AST and low-level core AST, let's just look no further than Haskell, right? So this is Haskell's surface level AST definition. It's part of the AST definition. So this is for expressions. This is the HS expert data type. And as you can see, this is a pretty large data type. It has almost 40 constructors. You have variable, unbound variable, and then going down, you have literal, lambda, and then a few more pages. Because like I said, in the surface language of Haskell, there are, there's very rich syntax, and there are many different ways of doing the same thing, and they all need to be reflected in the AST definition. So this is a large data type, and working with a data type like this can be pretty inconvenient because every time you want to inspect a value of this type, you may have to consider many alternatives, right? So basically working with this data type can feel like rewriting Haskell's desugarer yourself, which is far from a delightful task. Now compare that with this. This is GHC core. GHC core is Haskell's intermediate language. And this is the expression type in GHC core. And this is a much smaller data type. It only has 10 constructors. And so this is much easier to work with. So every time you have a value of this type, you only need to consider 10 cases. And you only have access to this GHC core language and the core AST if you're writing a compiler plugin. You don't have access to this from metaprogramming approaches like template Haskell. So this is core versus surface AST. And here now I have an example of QDSL, quoted DSL. So this is a paper by Phil Walder and a few others. This is from 2015, 2016, around that time. And this paper introduces the concept of QDSL in Haskell, and it gives a concrete example of a QDSL. And this is a code fragment from the paper. So if you're not familiar with Haskell, so this syntax of square bracket 2 vertical bars, this is the quotation syntax in Haskell. So this quotation is, like I said, it turns source code into ASTs that you can then work with. And then this two $sign syntax is called splice. So splice is basically the reverse of quotation. It turns ASTs back into code that you can then combine or splice with the surrounding code. And so that's how it works. And so this is what writing a program in this QDSL look like. And the paper claims that QDSL, in terms of syntax, is much closer to the host language Haskell. So it reuses much more of the host language syntax, where in EDSL, the similarity or the reuse is much more partial. And I definitely do agree with that claim, because if you ignore the metaprogramming stuff, the quotation syntax and the splice syntax, then this is pretty much just basic regular Haskell. Like this if then else is just a regular Haskell if then else, both in terms of syntax and in terms of semantics. There's just nothing fancy going on here. However, I think it's fair to say that this approach just adds a ton of syntactic noise to your program, because you're still not writing a regular program. You're basically doing metaprogramming all the time. And not only it is a challenge syntactically, it's noisy, but also like template Haskell is just something that is generally very hard for beginners to learn and to grasp. So because I mean this is so in that sense, this is not that much better than EDSLs, because if you think about it, EDSL and QDSL are actually very similar in the sense that they are both doing some kind of metaprogramming. So in EDSL, you're doing metaprogramming from the DSL point of view. So you're using your host language to manipulate the AST of your EDSL. So that's an EDSL. It's a kind of metaprogramming. And in QDSL, it's very similar. You're just using your host language's regular metaprogramming capability, like template Haskell, to manipulate the AST of your host language. So in that sense, they are very similar, or even you can say they are the same. And that's why they also have some similar drawbacks. For example, in either case, you're not really writing a simple or normal program in your host language. You're basically writing programs manipulating ASTs, and it shows everywhere in the syntax of the language. Now, on the other hand, here is an example of compiler plugin. This is a language called Plutus Tx, and it's the new name is Plinth. So this is another language developed by my team and my current job. So this is another surface language for Cardano smart contracts, just like Akin and Plutarch. This is Plutus Tx, and this is implemented as a subset of Haskell, and the compiler is a GHC plugin. And this is the part of the program written in Plutus Tx that solves the n-queens problem. And if you look at this for a second, if you know Haskell, I think you can tell that this is just pretty much basic, very simple Haskell. This is basically as plain vanilla and simple Haskell as it gets. And so this just makes it easy to onboard new users. Like if you're new to Haskell and you want to learn to write programs like this, it's really not as hard as many people think, especially, like I said, with the help of AI. So if you're new to Haskell, you have some questions about this kind of code, no problem. You ask ChatGPT or something like that. And it is pretty good at answering questions about any element in this code, right? And so that's just not the case for any of the other languages I showed you earlier, whether it's standalone DSL or EDSL or QDSL. I mean, at least not until those languages become sufficiently popular such that there is a sufficiently large amount of data for the models to be trained on. But for most DSLs, they're just never going to get there, right? And so I think this is really the main advantage of this approach, especially in the context of functional programming, because functional programming is already perceived as something that kind of has a steep learning curve. So I think to promote FP, it really pays to make things as easy as possible, rather than making things more complex. So this is the example of compiler plugin Plutus Tx. That's pretty much what I have. But before I wrap up, I do need to tell you about the drawbacks of this subset of general purpose language approach, because it is definitely not perfect. The main drawback, which is kind of a big one, is limited applicability. So this approach has more limited applicability. I think it's fair to say that it has much more limited applicability compared to standalone DSLs and EDSLs. Because in order for this approach to work, there's a precondition, which is there needs to exist a subset of your host language that is a good fit for your domain. But that's just not always the case. For example, if your host language is a functional language and you want your DSL to be a imperative language, then you can use an EDSL. That's no problem with that. But this approach is probably not going to fly, because you can't really have a subset of Haskell that is imperative, right? That's just not going to work. Another case in point is SQL. So SQL is a standalone DSL. But instead of writing SQL, you can try and write code interacting with your databases in a regular programming language. And that is basically what ORMs try to do. So what ORMs do is like they try to make it so that you don't have to write SQL, but you write something that is seemingly just normal object-oriented code to interact with your database. So in some sense, it's very similar to a subset of general purpose language. But the problem is the relational model and the object-oriented programming model, they just don't match that well. There's always a gap, right? So for simple things, that's probably okay. But as things get complex, that's inefficient or both. And I think that's why a lot of people don't like ORMs. They really just want to write SQL, write just plain SQL for that reason. So that's number one. Number two, plugin support. So this is specific to the compiler plugin method. So plugin support in compilers is often limited and unstable. So the Haskell compiler GHC, I think, is one of the better compilers for writing plugins. I mean, there are some other compilers for some mainstream languages that just don't support plugin at all. So Haskell compiler is one of the has one of the better support among the compilers. But even for GHC, the support for plugins is often limited and unstable. So the GHC API for compilers is for compiler plugins is kind of not very comprehensive and not very well documented, and it changes a lot from version to version. So that makes it harder to, for example, support multiple GHC versions at the same time. And that's why, the Plutus Tx compiler, the language I just showed you earlier, that compiler only supports one major GHC version at any given time because of this. So this is another challenge. The last one is your host language ASTs and compiler components may not be a good fit for your domain, because obviously your host language is not designed for whatever your domain is. So sometimes you need to fight with the compiler. For example, in the process of desugaring the surface language down to a core language, the host language compiler may be doing something that is doing some kind of desugaring that is not what. All right, that's all I have. And here are the links to all the languages I mentioned earlier in this talk. So check them out if you're interested. And that's it. Thank you for joining. And I hope this gives you some useful insights and takeaway on this topic. Thank you.